Hello, I'm Gage Garrity. My group members are Cameron, Kane, Brooke, Santagato, and Lauren White. And together, we're Team Safe Boom. Last summer, I, along with other Tulane students and professors, traveled to Peru with Tulane Biomedical Innovation for Global Impact. The purpose of this trip was to understand to engineer for better global health outcomes. To learn about the culture and healthcare system of Peru, we met with Dr. Valerie Paz-Soldan, multiple doctors in Iquitos, members of the Biomedical Engineering Department from Católica University in Lima, and most importantly, community members in Ayacucho, Peru. Ayacucho is an Amazonian river community 50 kilometers downriver from Iquitos. Our research relied most on the midwives in this community. Not only do the midwives assist with birth within the community, but they also act as first responders. Through conversations, we discovered that there are two large problems afflicting the community. First, the long travel times to receive care, and second, few solutions exist for maternal hemorrhaging other than bimanual massage before sending the patient on a boat ride to the nearest doctor. After returning to Tulane and explaining these issues to our group, we created our needs statement. Midwives in remote Amazon communities need a sterile way to control and monitor bleeding from postpartum hemorrhage in order to reduce maternal mortality.
After creating our first needs statement, we dove headfirst into the current research and design space for postpartum hemorrhage. Clinically, this form of hemorrhage is caused when the uterus does not naturally contract back down to its original size after childbirth, as shown here. The myometrium, or smooth muscle of the uterus, experiences atony, so the placental blood flow continues, and the patient loses blood at an unsustainable rate. We spoke to various professionals supporting maternal and child health in our community and abroad, including OBGYNs, epidemiologists, midwives, health department officials, and nonprofit and for-profit organizers. The biggest takeaway from these discussions was that postpartum hemorrhage is not preventable, but early identification of blood loss and mobilization of resources is imperative to survival.
We also researched prior art, provisional patents, and the current interventions. We found the most common medical device for postpartum hemorrhage is the Bakri balloon. However, as widely used as this device is, many doctors and nurses are not properly trained in how to use it, and it presents two major problems to low-resource communities. In particular, insertion requires ultrasound machines, and internal displacement of the balloon is not rare. So we set a primary goal to create a device that would help midwives curb uterine bleeding while transporting the patient to the nearest health clinic. Importantly, our device is not the end of clinical intervention for postpartum hemorrhage. From our readings and interviews, it was obvious that the best clinical treatment varies patient to patient and mainly relies on the doctor's opinion of the patient based on their vital signs. We cannot improve this aspect of treatment, so we focused on helping speed up the treatment process via muscle contraction stimulation. Then we brainstormed, drawing inspiration from unrelated products such as reversible umbrellas, childhood toys, and blooming flowers. We rapid prototyped to bring our ideas to life and settled on creating a mechanically based design that opens to apply force directly to the uterine walls. We also accounted for specifics that would enhance our prototyping, including applicable engineering standards, other reproductive health technologies such as IUD inserts, and postpartum uterus dimensions. However, because there is such little research on the state of the uterus directly after childbirth during hemorrhage, we bought the Mama U postpartum uterus simulator to give us a good scale representation of these dimensions and to test our design iterations. After creating our first prototype in Fusion 360, we 3D printed each piece in the makerspace and assembled it to show a robust design. We learned a few things from our prototype. The size was too large, the arms were too clunky and not sturdy enough, and we needed an applicator to facilitate insertion, similar to a tampon. To help our iteration, each member of our team analyzed one component of our product.
We redesigned our second prototype to the proper dimension scale and included more joints to facilitate the exact opening and closing motion we wanted. This time around, we spent more time focusing on the exact mechanisms of our device and how to optimize its function in such a small space. We also included a reusable applicator to ensure the vagina and uterus microbiomes stay separate and sterile. We began 3D printing this version of our product, only to realize that the dimensions were too small for the printers available. This, combined with Tulane's closure due to the COVID-19 pandemic, forced us to adjust the direction of our project toward a more computer-based modeling and testing instead of physical modeling. Before we tested our own prototype, we wanted to test the Bakri balloon to find the exact force value it creates to achieve a positive tamponade test, which takes place when bleeding ceases due to applied pressure. This occurs when the balloon is filled with 350 milliliters of water. We placed force-sensitive resistors inside the MAMIU simulator and connected them to an Arduino board, which displayed the data on a computer monitor. We inserted and filled the Bakri balloon and found it places 118 newtons of force on the uterine walls. This gave us a baseline number for our product to meet in its own testing.
We ran a static stress simulation test on the outmost plates of our device to determine if they could hold shape when subjected to the same force as the Bakri balloon. The test results showed that our device plates are able to withstand a force of 118 newtons with a factor of safety of around 8. Then we wanted to determine if our device could handle more force than the baseline requirements, so we reran the same test with 200 newtons. The stress profile is similar to that of the first test, but the maximum stress is greater.
We created a user guide that offers valuable information on how to operate the device. The guide is a simple pamphlet that describes the device's goal, instructions on how to insert and remove it, as well as safety concerns. After looking at the current market, we decided that polypropylene would be the ideal material for our device. It is biocompatible, lightweight, cost-effective, and considered the standard for reproductive health technologies. If possible, we would mass manufacture with polymer injection molding. Polypropylene costs 12.47 cents per pound. For just $1, we could produce 32 devices. Right now, we are 79% under budget. In the future, we will continue iterating our design to optimize its functionality. Ideally, we would create a final version of this product and bring it to Peru, where we would get user feedback from midwives about its functionality and aesthetic. This project would not be possible without the support of our many advisors, faculty, and sponsors. We would like to thank Drs. Raymond, Bayer, Paz-Soldan, Dansasek, and Ladley for their guidance, mentorship, and feedback, as well as the funding for this course. Thank you!